I'm sorry? Okay, so this will expand, and if there's no room for expansion, it would push it so hard that this would bend. And I've shown you pictures of that. So this would happen, okay? And trains would derail. And you have to do this in every structure. So for instance, you have to leave those gaps between the spans of a bridge. And if you don't leave that, then the bridge spans would warp and crumble. Yes. So you have to leave those expansion gaps. All right, so we'll find this gap. You need to, this gap is for this guy to expand, and for this guy, there's another gap there, and so on. Okay. So, and you saw that this would be the expansion of this length. Alpha is the linear expansion coefficient for the material, and this is the temperature rise. Okay, so this is made out of steel railroads. Okay, so let's look up alpha for steel. Okay, so there's coefficient of linear expansion for steel is 12 times 10 to the minus 6, okay, per degree Celsius. So the increase in length would be 12 times 10 to the minus 6 per degree Celsius, 10 meters, and for a temperature rise of 35 degrees Celsius. This cancels with that, and the increase in length would come out in meters. Okay, so this is, and this works out too. Okay, 12 times 35 is 420, 4,200. So 4.2 into 10 to the minus 3 meters, 4.2 millimeters, half a centimeter. So this much. The gap is about half a centimeters. Okay. And of course, okay. So where is the gap bigger, in Florida or in Alaska? Alaska. Wherever you see a larger temperature change, that's where the gap is larger. Okay. Yeah, we won't do this wrong again. And you guys saw that we talked about this, the crack, those cuts in the sidewalk, those are expansion gaps. Okay. So the same heat transfer into identical masses of different substances produces different temperature changes. Calculate the final temperature when 1 kilocalorie of heat transferred to 1 kg of the following. Okay, we'll do water and steel. Okay, so this will illustrate a point. So if you So what this formula says is, when you add heat to a substance, here's the specific heat of the substance. This is for solids and liquids. There's the mass of the substance. There's a temperature change. Okay, and so they want you to find the temperature change. What the problem is about is you're adding the same amount of heat, and higher the specific heat of the material, smaller the temperature rise. And I'm picking these two guys because the specific heat of water is about 7 times the specific heat of concrete. So you put the same amount of heat on water and concrete, the concrete specific heat is 7 times smaller, its temperature rise would be 7 times higher. Okay? So because the specific heat of water is so high, its temperature doesn't fluctuate as much. Okay, so the weather around a large body of water is always moderate. All right, so we have to look up the specific heat of water is so here's specific heat of water in joules per kg per Kelvin. And somebody look up specific heat of concrete while I write this down. Okay, let's do right in the middle. So 1,000, 1,000 and kg per Kelvin. Okay, so you see the specific heat of water is 4 times greater. So the temperature rise for concrete would be 4 times greater. Okay? So temperature rise for water is you're putting 1 kilocalories of heat transfer. This problem has mixed up units. Okay. By the way, 1 calorie is 4.186 joules. Okay. So the amount of heat is 1 kilocalories, 4.186 kilojoules. Yeah. And the specific heat is 4.186 kilojoules per kg per Kelvin. And the mass is 1 kg. Okay, so the temperature rise would be 1 Kelvin for water. If you put that much heat, 1 Kelvin is 1 degree rise in 1 degree Celsius rise in temperature. All right, the temperature rise for concrete would be, again, you're adding that much kilojoules of heat. The specific heat is 1 kilojoules per kg per degree Kelvin, and the mass is 1 kg. So the temperature rise is 4.186 degree Kelvin equal to 4.186 degrees Celsius. Okay, so temperatures, you need to have some areas at higher temperature and other areas at colder temperatures. What happens when you have this thing at higher temperature? This air warms up more than this air. Warm air is warm, when it warms up, it expands, it gets lighter, this air will rise. The pressure here is lower, pressure here is higher, and then you have breeze. Okay. And also, warm air rising, if it has moisture, all that moisture can condense there. Okay. So because of differentially, okay. So let's do one more thing. How does moisture get in there? When water evaporates, you have moisture in there. Every time 1 gram of water evaporates, it absorbs 540 calories of heat. So it's absorbed heat. When it gets to the clouds, that moisture condenses. Every time you have 1 gram of water condensing, it releases 540 calories of heat. Okay, so you see this transport mechanism of heat. So this heat released is what powers the hurricanes, which, okay. So the warm oceans evaporate water. This water vapor rising condenses, and that heat is released in the atmosphere, which powers the rotation of the atmosphere. All right. Anyway, differential heating is important if you want weather. Okay? And of course, if you don't want weather, then go live on a flat planet. Okay? That is perpendicular to the sun, right? If it's inclined to the sun, then you'll have problems again. I mean, you'll have weather again. All right. All right, so following vigorous exercise, the body temperature of an 80 kg person is 40 degrees Celsius. Okay, what's your normal body temperature? I'm sorry? 37 degrees Celsius, okay. If your body temperature is, rises to about 42 degrees Celsius for about 30 minutes, it's very bad news. Okay. So again, you want to cool down as fast as possible. Okay. So at what rate in watts must the person transfer thermal energy to reduce the body temperature to 37 degrees Celsius? Okay. So you want to get cooled down as fast as possible, and you're doing this in 30 minutes, assuming the body continues to produce heat at the energy rate of 150 watts. Yeah. Okay, so this is a real problem. Yeah, athletes face this. Okay, after a vigorous workout. All right. Okay. That's the specific heat of water. So what we have to do is we have to, how much heat do you need to remove? Okay, and over the time. Okay, so 80 kg mass times specific heat times the, okay. So here's the mass of the person, here's the specific heat of the person, which is, will treat people like water, and then that, okay. So that's 80 kgs. Specific heat is 4,186 joules per kg per degree Celsius. And you want to cool this person down by 3 degrees Celsius over a period of 30 minutes. A minute is 60 seconds. Okay. So this is the rate at which you have to cool the, this is the rate at which you have to lose heat to cool the person down from 40 to 37 degrees in 30 minutes. Okay. So let's calculate this. All right, 558 joules per second. Okay, so this is just to remove that excess heat, but you're also producing 150 watts. So you have to add that as well. So actual cooling rate. Okay, that's 5608,708 watts. So in the medical field, they use a trick. Okay, what needs to happen for your sweat to evaporate? When does your sweat evaporate? When the humidity is 0. then your sweat will evaporate fast. Okay, so if you heat up like this, what in the medical profession they'll do, they'll give you an alcohol rub. What's the humidity of alcohol? 0. You give an alcohol rub and that thing evaporates fast. And that'll cool you down. The only problem is, it's not a problem. When 1 gram of water evaporates, it takes away 540 calories of heat. When 1 gram of alcohol evaporates, it takes away about, I don't know, something like 200 calories of heat. Okay. So now you know, now you see why you sweat water and not alcohol. Yeah, so biological systems have optimized things. But in a pinch, you give yourself an alcohol rub. All right, so this is calorimetry. Okay, so this is a subject where if you wanted to find the energy content of something, so for instance, if you want to find the energy content of a food or a burger or something like that, you burn a burger, throw it in water, and find out how much it warms up, and that'll give you the energy. So a 1.28 kg sample of water at 10 degrees Celsius is in a calorie meter. So here's a calorie meter. It's just we'll use this in lab. So 10 degrees Celsius, 1.28 kgs. And then you drop a piece of steel that's at 215 degrees Celsius into it. What is the final equilibrium temperature? Okay. Okay, so what happens? You drop this warm stuff. So in calorimeter, you don't let heat escape. Okay, so all this is done in an insulating container. So this thing loses heat and the water gains heat. Okay, so the temperature of this one will drop and the temperature of water will rise. Okay? And what you'll see is the specific heat of steel is quite small. And so the final temperature will be very close to 10 degrees Celsius. That's the amazing part. Okay, so we'll calculate the final temperature. Okay, so the heat lost, that'll be negative, plus the heat gained, that'll be positive. The sum of the two is 0. Okay, let's say the steel thing loses 100 joules of heat, water will gain 100 joules of heat. So mass of steel times the specific heat of steel times the temperature change of steel. The temperature change of steel is negative because its temperature will fall down, plus mass of water, specific heat of water, temperature change of water. The temperature change of water is positive because its temperature will rise, and this should be 0. Okay. So let's look up the specific heat. Specific heat for steel is 448 joules per kg per. Okay. What is the mass of steel? 0.38 kg. 385 kg. And the final temperature of the steel minus the initial temperature, the final temperature will be lower, so this number will be negative. Yeah. Plus 1.28 kgs of water, 4186. And the temperature of water and so you can solve for the final temperature. That's final temperature, that's the only unknown. Okay, so I'm going to do this quickly. You guys can, so final temperature is 215 into 448 into 0.385 plus 10 into 1.28 into 4186 divided by 0.385 into 448 plus 1.28 into 4186. Okay, so that will be the final temperature. Okay, so it works out to 16.4 degrees Celsius. Okay, so again, this problem illustrates the high heat capacity of water. See, this is the heat capacity of steel, and there's the heat capacity of water. It's almost 11 times greater. Yeah. All right, so let's do these problems first, and then we'll come back to. So it turns out that it's very hard to extinguish crude oil fire using water. Yeah, so how do they, if it's hard to put out a fire using water, what do you do? I'm sorry? I'm sorry? You suffocate it. So if you can't douse the fire, what you want to do is you want to cut off the oxygen. So for instance, now for electric vehicles, those, if you spray water on electric vehicles, what will happen? Burning electric vehicles. The water will disassociate and you'll have more oxygen. What you want to do is spray it and cut off oxygen. Okay. Anyway, I mean, that's a common theme. If something is burning too hot, you want to douse it. What you want to do is you want to spray it with foam or whatever so that oxygen doesn't get to the object. Yeah. So each liter of crude oil releases that much heat. A liter is Again, this is half a liter. So 2 of these burning is releases this much heat. Calculate the number of liters of water that must be expended to absorb the energy released by burning 1 liter of crude oil if the water temperature rises from 20 to 100 degrees Celsius. So all this heat is released is used to warm the water from 20 to 100 degrees Celsius, then boil it, and then you warm the resulting steam to 300 degrees Celsius. Okay, you're going to do all of that. Now, in real life, that's not possible. So if a tanker is burning, you spray it with water. The best that will happen is it'll become steam, and then the steam will disperse away. I mean, if it becomes steam, that'll be good. All right. Anyway, this is being very generous. Okay. This won't happen at constant pressure. So we're going to release. We're going to try and douse a crude oil fire. Okay. So the amount of heat released is 2.8 into 10 to the power 7 joules. Okay, so what we're going to do is we're going to use this heat to warm water, then convert the water to steam, then warm the steam. So we're going to use all that heat to do these 3 things. Okay? And what we are finding is how much water we are going to use. Okay. All right. So the mass is the amount of heat divided by, so specific heat of water times the rise in temperature of water, latent heat of vaporization of water, plus specific heat of steam times the rise in temperature of steam. Okay, so this is the mass of water you're going to spray. And the amount of heat is 2.8 times 10 to the 7 joules. The specific heat of water is 4.4186 joules per kg per degree Celsius. What is the temperature of water going to rise by? 20 to 100 degrees Celsius, so 80 degrees. The latent heat of vaporization of water is 2.26 times 10 to the 6 Kelvin. And then the specific heat of steam is 2010 and you're going to heat the steam from 100 to 300 degrees Celsius, so 200 degrees Celsius. kg. Okay, so that's the mass of water you would need to deposit. And well, we want the volume. So volume is density is mass over volume. So mass over density, 9.34 kg. And the density of water is 1 kg per liter. Okay, so 9.34 liters. Okay, so even if the water absorbed all that heat, which it will not in practice, for every liter of oil burning, you need to dump 10 liters of water. Okay, and then you have another problem. What happens when you spray water on oil?
The oil rises because it's less dense.
That's right, water sinks below the oil. So you won't even be able to douse, the water won't even be able to absorb that heat. Okay. So putting out a tanker fire, an oil fire, is not easy. Okay. And in addition, that oil spreads out. If it's in the open ocean, it spreads out far and wide. Okay. Okay, what is the rate of heat conduction through 3 centimeter thick fur of a large animal? So that's an inch thick fur, having a 1.4 meter square surface area, assuming that the animal skin temperature is 32 degrees Celsius. So you see it's, skin temperature is that, and the air temperature is minus 5 degrees Celsius. And that the fur has the same thermal conductivity as air. Look at that. So you're assuming the same thermal conductivity as air. So the purpose of fur is just to trap air. Air is a poor conductor of heat. Okay, so it's not the wool that's keeping you warm, it's the air that's trapped that's keeping you warm. Yeah. What food intake will the animal need in 1 day to replace this heat transfer? Okay. So here's the animal, and what you want is to find the rate of heat loss. Okay, thermal conductivity, area, and this is the temperature gradient. Okay. Now again, we're taking this to be, we're taking the absolute value, so that's positive. So the rate of heat loss, so thermal conductivity for air, okay, somebody's got to look up the thermal conductivity of air. Hmm?
Yeah.
1025
1025.
watts per liter.
1,000 watts,
No, 0.025.
0.02. All right. Huh?
Yes, same thing.
All right, so that's Ka. Okay, so the thickness of the fur. So the skin temperature is 32 degrees and the outside temperature is minus 5 degrees. Okay. So K is 0.025 watts per meter per Kelvin, and per degree Celsius are the same. So area is 1.4 meters square, which is roughly the area of your body as well. The temperature difference is 32 minus or minus 5, which is plus 5, and divided by 3 centimeters, which is that many meters. Okay, so this is the rate of heat loss. We'll do it on the next page. All right, so let's do this. This is so 50 watts. Okay. So your heat loss is increased by 50% in cold weather. You remember your 100-watt bulb, and then in nice comfortable weather, and now you increase that. So if you were eating 2,000 calories, now you have to eat 3,000 calories. Okay. And so in the winter, if you're hibernating, you're not even eating. So what are the strategies that you would develop? You eat like hell before you hibernate. You store a whole bunch of fat. And then what else you do is the following. You decrease this temperature. You decrease your core temperature when you hibernate. And so you decrease your skin temperature. And so you reduce your heat loss. Okay? And all that calculation is done, because it knows how long it's going to hibernate and all that. It knows how much fat to store and all that kind of stuff. Now the strategy used is, what you do is you reduce your surface area. How do you reduce your surface area? I'm sorry? Yeah, you curl up, but also you become friendly with your friends. You huddle up. That's what penguins do. Okay. Yeah, but the outside guy is cold. The inside guy is warm. So what gives there? You switch. That's right. Okay, they've thought of everything. All right, guys, we'll stop here.